2.6, another type of way to solve differential equations, substitutions and transformations. So when we have the form mxy dx plus nxy dy equals 0, and we see that it's not separable, exact, or linear, it's possible to transform it into something else, similar by the integrating factors we did in 2.5. Okay, so in 2.6, we look at different types, and I'll go through each one. Look at homogeneous equations, Bernoulli, the linear coefficient, and in the form y prime is g of x plus b. I actually am not going to go through all of linear coefficients. It's just kind of too much stuff. This is one of those sections where if I ask you to solve one of these, I'll probably tell you what it is, like solve it, and it's, a Bernoulli equation or whatever. But I assigned the homework, and I want you to try it. So I'm going to go through these different types. So here's their general procedure. Identify the type of equation and determine the appropriate substitution or transformation. Excuse me. Rewrite the original equation in terms of the new variables. Solve the transformed equation. Express solution in terms of original variables. So you want to substitute back, basically. So let's take a look first at what they're calling homogeneous equations and see how to solve those. So homogeneous equations. Oops, it's going to underline the whole thing. And look at the type that they're talking about. Okay, so this is definition 4. So suppose we have dy dx equal to f of xy. So that is homogeneous. And there's different ways to define this, but this is, I think, the simplest way to look at it. It's homogeneous if f of tx ty equals f of xy. So it's almost like if you put that in, it cancels out. So to solve, this is what you do. So to solve, you let v equal y over x. Then you get, so then dy dx is equal to g of v. And we have, we make the substitution v plus x dv dx, kind of like it turns out to look like this, which I'll show you with an example, equals g of v, which is separable. So you convert to a separable equation. So you integrate 1 over g of v minus v dv equal to, and then you integrate 1 over x dx. Okay, then express this solution in terms of x and y. So then express solution in terms of, not sure where that came up. Okay, so that's the substitute back step. So let's look at an example of this. This is number 10. For some reason, I've been doing number 10 because it seems to be the ones that I want to check. So number 10 on page 76 in your book, Nagel 9th. Okay, so solve 3x squared minus y squared dx plus xy minus x cubed y to the negative 1 dy equals 0. So then, if you simplify that, you can, and make it separable, then you can do the substitution. So what you do is you rewrite this as dy dx equal to negative 3x squared, so you're bringing those terms over, plus y squared over xy minus x cubed y to the negative 1. Simplify that a bit. You get y cubed minus 3x squared y, xy squared minus x cubed. Then you make your substitution and simplify. So you get y over x cubed minus 3 times y over x, y over x squared minus 1. So if you do that, then it's homogeneous. So therefore, homogeneous and we can let u equal y over x. Doesn't matter the variable. Or y is equal to x u. All right, so then you, if you do the just substitution, you always got to do its derivative in something like this, right? So you have then that y prime by the chain rule is u plus x u prime. And we have that u plus x du over dx is equal to, and then you want to simplify that, u cubed minus 3u over u squared minus 1. All right, so now continue to simplify, separate variables, and we have, so separate variables, and you have x du dx equal to u cubed minus 3u over u squared minus 1 minus u equal to negative 2u u squared minus 1. So now simplify that and you get u squared minus 1 over u du equal to minus 2 over x dx. Okay, so now the variables are separated in the form you know how to integrate. So we integrate both sides. All right, so you get the integral of u squared minus 1 over u du equal to negative, took out the negative, integral of 2 over x, I guess I could have taken out the 2, dx. So simplify a little bit. You can divide both terms by the u, and you end up getting the integral of u minus 1 over u du, don't really need those parentheses there, equal to negative 2 integral of 1 over x dx. Okay, so then that's, this is if and only if. Okay, then that implies you get 1/2 u squared minus ln absolute value of u equal to negative 2 ln absolute value of x plus arbitrary constant. All right, and we'll just say plus 1 because we can redo it later. So now we can simplify that a little bit just to get in a better form. So if you multiply on both sides by 2, you end up getting a little nicer form, which looks like this. Okay, so you get this. Move this up a little bit. Okay, so you get u squared minus 2 ln absolute value of u plus 4 ln absolute value of x equal to c. Now, just like we did before, you can bring up the 2, bring up the 4, and get rid of those absolute values because you're taken to an even power, that kind of stuff. So this is if and only if u squared minus ln u squared plus ln x to the 4th equal to c. Okay, now you want to substitute back for xy, or with xy. You get the idea. So you substitute back, and you have y over x raised to the 2nd minus ln y squared over x squared plus ln x to the 4th equal to c, and then you can continue to solve. You get y squared over x squared minus ln y squared over 6 to the x to the 6th equal to c. So you're just combining this and this with this negative here. A little bit of algebra. Okay, so that's your technique. For most of these, I wouldn't do these unless I told you to. Use this technique to solve. Okay, we'll go ahead and pause and do another one. I think we'll do 2 after this. Do the next cases.